So, sorry again for last week's hiatus. Hopefully all of you kind of watched these videos. It was kind of the introduction and kind of me working through hypothesis testing. So what I'm going to try to do today is do like a synopsis or a summary of that, work through examples of hypothesis testing problems or kind of how we do this by hand. I'll also try to give kind of a little bit of more of a comprehensive view on what we did for this kind of third of the class going into this next exam. And then Wednesday, we'll do a little more of exam review, looking at problems from those practice exams that are up on Canvas. My guess is, people looking through those, you have questions on Wednesday. My guess is we'll probably do a lot more of hypothesis testing, but we can also do some of the older material as well. Also, before I forget, so I had a couple of people ask, this practice problems, it is, I know it says it has points. I can't turn that off for whatever reason. It's not a feature. It's you don't have to complete this. You don't have to do this if you don't want to. It's just some problems I put together from that Connect platform that if you want some additional practice working through some hypothesis testing problems, you can find those there, right? Now, if you're studying for the exam, my suggestion would be go through the practice exams first. And if you really want some more problems for hypothesis testing or contact intervals, then maybe start taking a look at these. Okay, but it's not any points. You just practice problems if you want to do them. If you can. If you don't have to. Okay. Any other questions for me before we kind of jump into things here? So what I'll be doing today is using this HT example 2023 blank that's up on Canvas. I'll also be kind of going through how we do this in hypothesis testing Excel, while also simultaneously doing it on the board so we can kind of connect those two, right? So before I do that, I want to try to kind of summarize what we've been doing. So I'll mark this down. So we started out a long time ago, and this is kind of like the very beginning of the Excel assignment, right? It goes all the way back to like when we were looking at the Indiana weather data. We're just starting out with a normally distributed variable. We know that variable should be kind of distributed around whatever that true population mean is. Right? We then said, okay, look, if I wanted to turn these into z-values, right, how would I do that? Well, I would just take some cutoff value for x, right, subtract that mean, and then divide by my standard deviation. So I can map this down to some z-value. We then kind of said, okay, in practice though, I don't know the population mean. I can't observe that. I usually just have a sample mean. So we said, okay, what's true about the distribution of my sample means? Well, they should be normally distributed around whatever that true population mean was. Right? So the mean of my sample means, we said, was just the original population mean. We also said the standard deviation was what? The square root of the original variance over my sample size. So when calculating z-values here, we took some cutoff value for our sample mean. To turn that into a z-value, we subtract the mean of my sample means and then divide by the standard deviation of my sample means. However, we know the mean of my sample means was just the original mean of the data we sampled from. And then we have an equation to find the standard deviation of our sample means, which is just square root of the variance over the sample size. Okay. We then started to look at things like confidence intervals and now hypothesis testing. So with hypothesis testing, we're still thinking about, we take a sample and we see some sample mean, right? We then might say, okay, look, this should be centered around whatever the true population mean is. But with hypothesis testing, the whole point of taking a sample is we didn't have the population data. We don't know what the population mean is. So we're going to assume kind of this mu subscript 0. This is just an assumed true value for that mean. So if I assume, that the true mean income is 50,000, my sample means, if I'm taking samples and calculating the average income from those samples, should be centered around that assumed true value if that value is in fact true. right? If what I assume to be true is in fact true, my sample mean should be distributed normally around that assumed true mean. The only thing that's going to change when we want to try to calculate a z-value now is I don't have the true population mean, I just have an assumed true mean. So it looks exactly the same. We're just using an assumed true mean now. And instead of just calling this a z-value, we kind of give it a more fancy name, which is it's our test statistic or our z statistic. That's really just, the difference in terminology is saying, well, look, we weren't subtracting the true mean, we were subtracting the assumed true mean here. Okay? So now it's not the number of standard deviations away from the true mean, it's the number of standard deviations away from the assumed true mean. It's really kind of, not that much different. Okay? What we then wanted to do is say, okay, look, what's the probability that if what I assumed to be true was in fact true, what's the probability I saw the sample mean that I did, or anything even further away from that assumed true value, right? The name that we had for that, the probability that I saw the sample evidence that I did that was as inconsistent with what I assumed to be true, or anything even more inconsistent, that's going to be our p-value. The probability that we saw the sample mean that we did, or anything even further away from that assumed true mean. Once we have that p-value, we're going to say, okay, look, just like with confidence intervals, if that probability gets small enough, what's probably true is, like, let's say I get, the probability I saw the sample mean that I did, if what I assumed to be true was in fact true, that's like 0.0005. Well, that's a really low probability. What's probably true is that what I assume to be true is wrong, right? It's probably more likely that the true mean, is somewhere over here, right? So if this p-value gets less than these threshold alphas that we're going to set, then we're okay rejecting whatever we assume to be true, right? If that probability gets small enough, the likelihood that we saw the sample evidence we did gets really, really small, we're okay rejecting that assumed true mean because it probably wasn't right? We're probably wrong. What values are we going to use for our alphas? It's the same thing as what we're doing with confidence intervals. I've got the 90, 95, 99% benchmarks. Those correspond to alphas of 0.1, 0.05, and 0.01. So we'll work through a couple examples doing this, kind of turning our sample means into these z statistics, finding the probability we saw something that many standard deviations away from the assumed true value, or even further away, or our p-value. We'll then say if the p-value is less than alpha, we're okay rejecting. Okay. Questions before we kind of jump into an example here? Anything I have? And we'll go through kind of how we identify alternative and null hypotheses as well. So we've really got three types of examples. You've got situations where you have a sample mean and the population variance, or the population standard deviation. Or we could be looking at proportions. Both situations, just like confidence intervals, we get to use that standard normal or that z table. If I've got a sample mean and I only have a sample variance, this is where I have to use that student t table. Okay. Excuse me. So we'll work through one of each type of example today. And we also have different types of hypothesis tests we can do. We said we have kind of a left-tailed, a right-tailed, and a two-tailed test. Two-tailed test is probably the hardest. That's the one we're going to start out with. And we always name the test based off the alternative hypothesis. So as I walk through these, I'll kind of help identify this and kind of go over that. So let's blow this up and start with this example. So I've got some data here. I've got BMI, and I calculated the average, right, of my sample data. So I found the average BMI. Let's assume that we have some known population variance, right? We said this isn't probably as likely in practice, but we got to walk before we can run. So assume that we have this known population variance, and then I use that count function just to find my sample size. Hopefully this is, stuff we're getting pretty familiar with. I then kind of typed out the hypothesis test that we want to do. So here, let's say I don't know, I'm concerned about the health in the US, and I'm like, is the true BMI something different than 32? Okay. So what I want to test for is my alternative hypothesis, right? So anytime I'm looking at a problem, whatever I'm trying to test for, whatever I'm trying to find, that's my alternative hypothesis. I'm then going to stack the deck against myself and assume the opposite or the complement is true. So if my alternative is that it's not equal to 32, I'm going to assume that that mean is 32. Right? So I'm stacking the deck against myself. You know, whatever I'm trying to find, I'm assuming the opposite is true. So here, we would say this is a two-tailed test. I've got a not equal to sign. So that means evidence that would go against my null could be on either side, right? I could see a sample mean of 28, that would go against my assumption. I could see a sample mean of 37, that would go against my assumption, right? So evidence on either side goes against my null when I have a two-tailed test, and when I have a not equal to sign in that alternative hypothesis. So if I think about what's the distribution of my sample means going to look like, well, if what I assume to be true was in fact true, they should be centered around that value of 32. Right? If that is the true mean, if what I assume to be true is in fact true, my sample mean should be normally distributed around that value. Well, I took a sample and I found what? 29.5 approximately. Right? So I could turn this into a z value or a z statistic, look that value up in the table would give me the area to the left, right? Which usually we would think represents our p-value, right? The probability that I saw sample evidence that was as inconsistent with what I assume to be true, or something even more inconsistent, right? Or sometimes I'll say anything more extreme, right? That way you don't have to worry about like negative values. It's actually less than, right? Because it's a larger negative value. Just more extreme, right? Or more inconsistent with that null. The problem is that with a two-tailed test, and this is sometimes if you're drawing this out to kind of help you remember, always when you plot this stuff, with a two-tailed test, it would have been equally as likely, if I'm only taking one sample, it's equally as likely I could have seen something on the other side of the distribution that was as far away from that assumed true mean. And now all of these values also go against my null hypothesis just as much as every value in this range. So for a two-tailed test, yes, we only have one sample, but we know that any value over here that I could have seen, it would have been, if I could have taken another sample, it would have been equally as likely for me to see sample evidence on the other side that also went against the null. So I can find this area to the left, but it doesn't represent my p-value. It only represents half of my p-value. So how do I get my p-value? Multiply it by 2. Right? So that's the additional step we have with a two-tailed test is we can find the area in our tail, right? We then have to multiply by 2. Right? Or the probability that I saw sample evidence that was as inconsistent with the null as what I saw, or anything even more inconsistent. And remember, oh yeah, they have all the, they have counterparts on the other side that also go against the null. So how do we do this? We already had this up here from before, right? I'm just turning this into a z value. I'll take that sample mean, 29.5, subtract the assumed true mean of 32, right? Divide by my population variance, which was what, 60? And then divide that by my sample size of 145. So I could just, that's just a matter of plugging things in and getting it typed into my calculator. So what I'm going to do is show you how to do it in Excel. I'm just going to use Excel to be my calculator, right? I'm going to take that sample mean, and I'm going to subtract that assumed true mean. Then I'm going to divide by the square root of my population variance divided by my sample size. Just using Excel to be my calculator, clicking on the cells where those values are, I could have very easily just typed those values into a calculator. So that's nothing crazy, right? We're just using Excel to be our calculator up to this point. So this should give me my test statistic, right? So I get about negative 3.89. Now, we might not be super familiar with all these values yet, but it's pretty far away, right? Test statistics over 2 are pretty large, right? So I've got something that's 3.89 standard deviations below. What's the area to the left of that going to be pretty close to? 0, right? If I multiply something very close to 0 by 2, I'm going to have something very close to 0, right? So I've pretty much have a p-value that's really close to 0. So what levels can I reject at here? Well, would a p-value of 0 be less than 0.1? Yeah. So we would reject at the 90% confidence level, or sometimes we would say we reject with 10% significance. Significance, when we kind of use that terminology, it's really just whatever's, the complement of your confidence interval, right? So 90% confidence, 10% significance. Can I reject at the 95% confidence level? Well, 0 is less than 0.05, so yes. So I can reject with 95% confidence or 5% significance level. Can I reject with 99% confidence? Yes, right? 0 is less than 0.01. So I can reject with 99% confidence or at the 1% significance level. Now, if I actually want to do this by hand, I'd go to my Z table. I've got my test statistic of negative 3.89, negative 3.8, 0.0001, right? So I can actually be even more precise. So 0.001, multiply that by 2. I've actually got a p-value of 0.0002. That's still going to be less than my alphas, right? I knew it was close to 0, pretty close to 0. And so it's going to be less than all my alphas. I can reject at every single confidence level. Any questions up to this point? So, what do I want to do there? I think I'll show you how to do this, and then I'll change something here. So our table is constrained to 2 decimals, and then it rounds everything to 4 decimals when it shows us the probability. So we're going to see that actually, if we could be a little more precise, in Excel, we'll get something that's a little bit different from this, right? Because it's just going to be a little bit more precise. So if I have a z-value and I want to find the probability of seeing that z-value or anything below it, right? The area to the left, we already have a function we've used for this. It's just that norm.s.dist function, right? I tell it a z-value, it essentially does the integration for me, or looks that value up in the table, spits back out at me the probability, or the area to the left, the cumulative probability. So all I have to do is tell it that z-value, and then we said we always kind of use this cumulative option for this function, so comma 1. So look up that z-value, give me that cumulative probability of the area to the left. Right? Now that won't quite be my p-value. I still have to do what for a 2-tailed test? Yeah, multiply that by 2. So I can do that all in one cell, right? Just multiply whatever that probability is by 2. Now, this is going to look a little bit weird because why is it 0.001 and I found 0.002 from the table? Well, I'll kind of show you. If I get rid of this multiplied by 2, the area to the left was actually 0.00005, which it then rounded that up to 0.0001. Right, so it's a pretty big rounding error, but it's because we're out to the 4th decimal, right? So in Excel, we can just be a lot more precise than we can with that table, especially when we're dealing with really low probabilities, right? So here, it doesn't really change anything because that p-value is still less than all of our alphas, right? But yeah, we have this really low probability that, look, if what I assume to be true isn't that true, the probability I saw sample evidence that was as inconsistent with that null hypothesis as what I saw, or anything even more inconsistent, only about a probability of 0.0001. It's pretty low, which probably means the true mean is probably a lot closer to the sample mean that I found, right? So one thing that we can do in Excel as well is use this built-in if function, right? So this is kind of a neat function. I mean, it has a lot of uses. You can do a lot of different things with it. For us, it's going to be pretty simple. All we want to do is, well, I'm trying to figure out if I reject or not. Here's my rejection decision. Is that p-value less than alpha? Get this ingrained before Friday, right? We're always going to reject if that p-value is less than alpha. So all I'm going to do is say, well, look, if this cell that has the p-value in it is less than the cell where I put alpha, comma, if that holds, if that's true, I know that I should be rejecting. So put the word reject in this cell, right? Check to see if this is true, comma. If it is true, what do you want this cell to have? Well, I want it to have the word reject. I have to put that in quotation marks. That's just lets Excel know it's a number, it's text, right? Comma, if it's false, what words do I want to be in that cell? Fail to reject, right? Now, this is kind of where I sometimes get questions. why this is. It's because so we don't say that we accept the null, we just say that we fail to reject it. Because in this case, right, I did find evidence that was inconsistent with the null, so I shouldn't necessarily be accepting it, but it wasn't inconsistent enough to where I could reject it. So we kind of use this term of we fail to reject, as opposed to saying that we accept the null. So if I hit enter here, if I've done this right, hopefully right, I get reject. This is a really small p-value. We said we should reject at every single level. I'd use an alpha 0.05 here. Sure enough, we can reject. Okay? And if I wanted to, I could play around with 0.01, right? I can still reject the 99% level. What about the 99.9999999%, right? Well, maybe if I, go that high up, okay, now I can't, I failed to reject at that high of a confidence level, but that's also an absurd, right? That would just be kind of, I can't really say anything with 99.99999% confidence. So we use these more traditional benchmark values, 0.01, 0.05, and 0.1. Okay. Any questions on anything here? We'll see it sell again or have a question on any one of the steps along the way. Okay. So what I want to do now, I'll wait and do the next example. So we can reject this assumed true value of 32. I can say that the true BMI in the US is not 32, right? Based off the sample evidence I found. Well, can I reject 31? Right? So I can start playing around with different values. Well, a sample mean of 29.5 wouldn't be quite as inconsistent with my assumption if I assumed it was 31, right? It's a lot closer to that. I actually failed to reject the 99% level. Based off the sample evidence, I can't reject that the true BMI is equal to 31, right? Excuse me. So I could, in any example, I could play around with this hypothesized true value, figure out, what values can I reject, what values would I fail to reject based off the sample evidence I found. Okay. Any questions on this before we move to the next example? Yeah.
So on like a single
only difference is you wouldn't multiply by 2. In fact, I'll go through what we're going to do next. We're going to do a left and a right tail test. Okay. So we'll do, I'll go in different order. Let's do this one. Well, no, I want to do this one because I think it's a little bit easier to transition from. But I think this is a left tail test. I was kind of hoping to do a right tail, but it's fine. Left tail, one tail test. So we'll get an example of this. So this other data set, mean sample variance. So here I'm looking at that e-cigarette or vaping data. So this is like the age they first, the student first tried an e-cigarette. All I did was find my sample mean, sample size, and then now I didn't have a known population variance, so I used that var.s to find my sample variance. So I've got a situation now that looks a little bit different because I no longer have the standard deviation of my sample means. I now write kind of with an S, kind of representing, I calculated that standard deviation with a sample variance as opposed to a known population variance. What else is that going to change? Well, it's no longer a Z value. It's now going to be a T value. And I have to use that student T distribution. So let's work through one of these. I've got this idea where I'm like, okay, how young are people kind of trying these e-cigarettes? I'm going to want to see, okay, is the true mean age, that someone first tries an e-cigarette less than 14, right? That's what I want to test for. So I assume the opposite is true, or my null hypothesis would be that the true mean age is greater than or equal to 14. Okay. So here I've got a less than sign in my alternative hypothesis. So the sign of the alternative hypothesis tells us what type of test. So here I've got a less than sign. I have a less than or a left tail test. Only evidence on the left side of my distribution would go against the null, right? So I'm thinking about this. My sample means, if what I assumed to be true was in fact true, should be centered around that value of 14. Only evidence on the left side would go against the null, right? If I found a sample mean of, 15.5, I don't even have to do the rest of the hypothesis test. I know my rejection signal, right? If I saw 15.5, well, that supports the null. Why the hell would I reject it, right? So anytime we find evidence that's consistent with the null, I'm done. I don't have to really go through all these steps. I know that I'm going to be failing to reject, right? I found something that supports it. So here for a left-tailed test, only evidence on the left side would go against the null. I could then say, okay, what's my p-value? Well, now it's just the area to the left of that value that I found. So here we found what? A sample mean of 13.68 about. So I did find sample evidence that was inconsistent with that null, right? It's not greater than or equal to 14. It's in fact less than 14. It supports the alternative hypothesis. But is it inconsistent enough? So this is kind of a tricky one. You look at this and you might think, well, I mean, this value is really close to what I assume to be true. What I assume to be true probably is true, right? But we'll kind of work through the mechanics and see that, you need to take, be careful, right? Because it's not the distance away from what we assume to be true. It's how many standard deviations away are we, right? And if we notice here, what's true about my sample size? It's really large, right? 3,500. So if I have a really large sample size, what's going to happen to that standard deviation of my sample means? Denominator is larger. Divide by a larger number, it's going to be really small, right? So high sample sizes make the variance on my sample means really low, right? Which means it's not very likely I see values far away from that true mean. So even seeing something that's like 0.32 away from that assumed true mean, it might be a high number of standard deviations away. So how do we get this? We use Excel to be our calculator, right? We've got that function. It looks exactly like what we did for the previous problem. The only difference is we use the sample variance instead of a known population variance. So I'll take my sample mean, subtract that hypothesized true value for the population mean, divide by the square root of my sample variance divided by my sample size. It literally is like, it's the same setup we had before, just I have a sample variance now. So this will no longer represent a Z value or a Z statistic. This test statistic we'll kind of call a T statistic. It's coming from the student T distributions. So I hit enter here. And sure enough, even though I was only 0.32 away from the assumed true mean, 0.32 was 9 standard deviations away. And that's because the standard deviation was probably really, really small. Where is it? There it goes. I had a really high sample size. Okay. So in practice, I'm going to show you something that lines up a little bit more with the exam. So like on the exam, I might ask you, I might give you these values, ask you to find the test statistic. The next problem, it's like, well, this is really, really large. I know this p-value is going to be pretty close to what? I'm going to have to look it up. Here. Yeah, right? On the previous one, we had a test statistic of negative 3.8, and we had almost an area of 0. Negative 9.4, we're even further down in the tail there. It's going to be really small, right? So we know that we're probably going to be rejecting that. I'm going to give you one that's a little more interesting. Let's say on the next problem on the exam, what I would do is, okay, look, whatever test statistic you found, assume that instead it was this value, all right? And I'd give you something like negative 1.664. And then I'm also going to change one more thing from this example, which is in practice on the exam, if I have, I don't like this. I feel like Big Brother's watching right now. If you don't know what I'm talking about, this is turned on and now the camera's following me. So, lost my train of thought. Oh, so if I had a really high sample size, if I was doing this in practice, I would have to know my degrees of freedom before I went to that T table. Well, 3,573, my degrees of freedom is just n minus 1 or sample size minus 1. So 3,572. If I look at that student T table and I go down here, I mean, when I get to really high degrees of freedom, it starts jumping a lot. I mean, it stops at 1,000 because by the time I get to 1,000, we said as that sample size goes up, the degrees of freedom goes up, my student T is so close to an approximation to the standard normal, we can just use the standard normal. So I'll give you something that's a little bit more realistic for what I would ask you to do on the exam. which is, let's say we found this from a sample size of 81. Now notice, when I went to a smaller sample size, that should have increased my standard deviation, which if I'm now dividing by a larger number, made my test statistic much smaller. So seeing the same sample evidence, but from a smaller sample, we won't have as high of a test statistic. And that's because our sample size influences our standard deviation. So, before maybe the standard deviation was 0.001. Now, if it's 0.1, right, well, I'm going to be much, fewer standard deviations away. So let's say I have the sample size of 81 instead. So my degrees of freedom should be what? Yeah, it's just n minus 1. So 81 minus 1 is 80. What I'll then do is say, okay, go to my student t-table, look up that degrees of freedom of 80, and now I need to find that test statistic. Now here's one other kind of flaw, I guess, with the student t-table that we can kind of see we can remedy in Excel, is that it only looks at the right side of the distribution, gives us all positive values. But it doesn't really matter because, if I think about it, the area to the right of positive 1.664, if this is a symmetric distribution, the same as the area to the left of negative 1.664. So, this is not a two-tailed test, so I'm going to get rid of this to not cause any confusion. So I'll try to find 1.664 in my table at the degrees of freedom of 80, right here, right? I then go up, right? So 1.664 corresponds to an area of 0.05 to the left. So with confidence intervals, we had some examples using the student t where we knew the area in the tail that we wanted. And then we went down to our degrees of freedom to find what t-value corresponds to that. With hypothesis testing, we're going to know the t-value, and then we have to go up to the column heading to find out, well, what's the area in the tail associated with that t-value. So we're kind of working in opposite directions, confidence intervals as opposed to hypothesis testing. Excuse me. Any questions on this before I keep moving? So with this p-value, what levels can I reject at? Can I reject at the 90% confidence level? Well, yeah, it's less than 0.1. Can I reject at the 95% confidence level? This is tricky, right? 0.05 isn't technically less than 0.05. So I'd actually fail to reject at the 95% level. And if I can't reject it with 95% confidence, definitely can't reject it with 99, right? It's not going to be less than 0.01. So here, kind of giving you something that might be a little more like what you see in the exam, I'll give you an assumed true test statistic so that it will be one of the values in this table. Right? You'll never have to be like, well, I'm in between these two, so my p-value, put it in a range. I might expect you to do that on the final. Kind of we'll work through some more hypothesis testing stuff after this exam. But for now, I will give you a test statistic that is one of the values in this table. Okay. Any questions on that before we jump back to the Excel data? So, there it goes. How can I find my p-value in Excel? Right. Well, instead of using the normal distribution, we now need to use the student t distribution. So we'll use t.dist. It works the same way. We tell it the test statistic, comma. The other thing that we now need is, well, what's my degrees of freedom? It's my sample size minus 1. And then just like the norm.s.dist, we always put comma 1. So it's giving us that cumulative probability of that area to the left. And for a one-tailed test, for a left-tailed test, that's all I want. That's my p-value. I don't have to multiply by 2 because evidence on the other side now does not go against the null, right? It actually supports the null, right? So I'm only concerned with kind of evidence that it goes against my null. So for a one-tailed test, all that area is in one tail. So I hit enter. I get about 0.079. Once again, I can just be a little bit more precise. I didn't have to, or actually, sorry, I'm using a different test statistic here because I gave you an assumed true one. Just to kind of prove to you. Right, we get about 0.05, like just like if we looked it up in the table. But the actual one that we have from the data, a little bit higher, same kind of thing though, 0.07 would be less than 0.1, not less than 0.05 or 0.0. And then I could do the rejection decision the exact same way. just using that built-in if statement and say, look, if this p-value is less than, here I chose a pretty high alpha value of 0.1. If it's less than 0.1, comma, put the word reject, comma, if it's not true, put the words fail to reject, right? So it's the exact same setup as what we did in the previous problem once we get to this point. Once we have our p-value, rejection decision, doesn't matter if it's a student t, standard, normal, our rejection decision is just, is that p-value less than this threshold alpha that we set, okay? So here, 0.07 is less than 0.1, so I reject. And then if I wanted to play around with this, well, can I reject with 99% confidence? No, I can't, right? Questions on that? Everybody get this okay? Should be exactly what we had before, yeah.
So are you only using the t-values when it's a one-tailed?
So the type of tail test, I just chose one. So I can have a left, right, or a two-tailed test for any of these three examples, right? It's just that I'm using the student t because I only had a sample variance, not a known population variance. But I could do a left, right, or two-tailed test for any one of these types of examples. In fact, we'll have one more that we go through next, which will be our sample proportion, right? There, we're using the standard normal distribution, even though I'll show you an example where it's a one-tailed test. So the type of test doesn't influence what distribution you use. It's just how you find that p-value, that area in the tail, varies a little bit. You know, if it's a one-tailed test, it's all in one tail. If it's a two-tailed, we then have to multiply by 2. But you'll look that area up from different distributions, depending on whether or not you have a known population variance or if you only have a sample variance. And then if you have proportions, those are always easy. We always use the z-tables there. Always use the standard normal. It's a good question. Any other questions before we keep moving? I know this is a lot, so bear with me. So I'm going to go back to using this count function just to make a point. So I'm going to find a much higher sample size here. So what should be happening? From the same sample evidence, if I have a higher sample size, seeing something that, you know, the same distance away from my assumed true value, but my standard deviation is going to be much smaller, right? So that same distance might be a higher number of standard deviations away, or increase that t-value. When I say increase it in magnitude, right? If it's negative, it becomes a larger negative value. Well, if I push this out further, I'm going to be getting a smaller area in the tail. So if I take this really high sample size and found the exact same sample mean, it's going to end up having a much lower p-value. So if I hit enter here, sure enough, my p-value is like 20 zeros and then a 2, right? They're very, very small. So this kind of shows if I have really high sample sizes, I can reject things at very high levels of confidence, even when the sample evidence I found was pretty close to that value, right? In fact, can I reject, no, not 14, 13.8. I mean, I'm really close to 13.8, but I can still reject that value with this really high sample size. Okay? So I'm really trying to stress the importance here of having high sample sizes, because it really allows me to pinpoint down, you know, if I can reject, you know, values that are not even very far from what I found for my sample mean, I can get a pretty narrow range, just like with confidence intervals. Higher sample size, I can get a narrow range of where that true population mean is. All right, I'll change this back to 14, so when I save it, everything kind of lines up with what we did. So we're then going to move to hypothesis testing for proportions, okay? So I had this kind of variable, which is a 0, 1, which is, did the student ever use an e-cigarette, right? And maybe I'm concerned, and I'm like, okay, look, is the proportion of kids who have used an e-cigarette, I think these are only middle and high school students, oh, sorry. Is that true proportion, no, greater than 0.15, right? So I want to know, you know, I'm maybe pessimistic. I think that more than 15% of kids have tried e-cigarettes, right, in middle high school. So I assume the opposite is true, and I stack the deck against myself. I assume that it's less than or equal to 0.15. So here I've got a greater than sign of my alternative hypothesis, or I've got a right tail test. And that's because only evidence on the right side of 0.15 would support the alternative and go against the null. So we have to change things a little bit because I can't use the Z formula for a sample mean. I've got a sample proportion. So we go back, kind of remember, how did we turn sample proportions into Z statistics? Our equation looks something like this, right? A little bit different from our sample mean, all right? But we still subtract, take our sample statistic, subtract the population value, divide by the standard deviation of that sample statistic. It's just now that standard deviation has a slightly different formula. Now, one problem with this is, unlike the previous examples we're looking at, we no longer know the true population proportion. But just like the sample mean, and I didn't know the true population mean, I just use an assumed true value for that population proportion. Okay. What's that assumed true value in our example? 0.15, right? That value comes from that null alternative hypothesis. That's what we use for our assumed true proportion. So what should be true is my sample proportions should be normally distributed around that value of 0.15 if what I assume to be true is in fact true. Okay. Everybody with me up to this point. So I had that 1, 0 variable. All I did, right? The sample proportion is this unique case of the sample mean. It's when I take the mean of a 0, 1 variable. So I just took the average of that variable. I've got an enormous sample size here. So probably you can already guess, if I got a really large sample size, it works the same way as it did with sample means. A really large sample size decreases the standard deviation. I'm decreasing that standard deviation in the denominator, increasing my test statistic, making my test statistic really far out here. I'm gonna have a really small area in the tail, right? But we'll work through the example. We'll just work through it. And even we might change the sample size later to kind of see maybe it's a little bit more interesting. So all I'm gonna do, same thing, use Excel to be my calculator. I've got everything I need, right? 0.15 is my assumed proportion. 0.181 is my sample proportion I found. Sample size is like 20,000. So I'm just going to say, take the sample proportion, subtract the assumed true proportion, divide by the square root of that assumed true proportion times 1 minus that assumed true proportion divided by my sample size. Right? Once again, just using Excel to be my calculator here. I could have typed all these numbers into my calculator. I think it's a lot easier just to select the cells that they're in. Right? Now, if I hit enter here, I'm going to have a problem because I forgot to do something, right? What did I have? What do I have wrong here? My hypothesized true value shouldn't be 15. It should be 0.15. I just typo. So I'm going to go back up here. We have to change that earlier. Just 0.15, right? So I get a pretty large test statistic. I take 12, right? So dealing with proportions, that test statistic comes from that from that standard norm or the Z tables. Right? So I found sample proportion of 0.18 approximately. That's what a Z value of 12.51. I don't even have to use the table. If I look this up, remember, I have a right tail test now. So I actually want the area to the right when I'm thinking about my p-value. Because my p-value is the probability I saw sample evidence as inconsistent with what I assumed to be true as what I found, or anything even more inconsistent, right? Well, now more inconsistent is to the right, right? Because only evidence above 0.15 would go against that null. So when I look this up in the table will tell me the area to the left. So if I want the area to the right, what do I have to do? Yeah, it's 1 minus that, right? So this is where I think drawing it out, like especially right-tailed tests, can kind of help you remember, oh yeah, the table always gives me the area to the left, I need the area to the right. Okay. Let's say I did have a smaller sample size here, just so I have a little bit more interesting. I just want to kind of show you how you would do this by hand. And we can't find 12.1 in the table because it's a really high number of standard deviations away. So let's say I only had a sample size of 100 and my test statistic was what? 0.88, right? So instead here, assume that we found a test statistic of 0.88. So I go to my standard normal table or my Z tables. I look up 0.88. So go down here, 0.8. 0.8. So 0.8106. But that's not my p-value. I still need to subtract it from 1. So we get what? 0.1. Yes. Okay, I'm doing math in my head correct here. Right? So I've got a p-value of about 0.18, right? So here, what levels could I reject at? I mean, this is, I feel like I could ask this to, I mean, is this value less than this value? No, right? 0.18 is not less than 0.1. I failed to reject, right? Is it less than 0.05? Well, no, it's not less than 0.1. It definitely can't be less than 0.05. And it can't be less than 0.01. So I failed to reject at every single confidence level here based off of the p-value that I found. Okay. Any questions on that? So hopefully once you get to this p-value part, like that's going to be some questions. Those should be easy ones. Like all you're doing is that p-value less than alpha? If it is, you reject. If it's not, you fail to reject. Let's go back here. I'll show you, finish this up. So if I'm doing this in Excel, I'm now using that standard normal distribution again. I have this z value. However, I only have this ability with this norm.s.dis to find the area to the left. If I have a right-tailed test, I had one more step, which is, yeah, I can find the area to the left of my test statistic, but that's not my p-value. My p-value is actually the area to the right. So I have one more step, which is subtract it from 1. Right? Now this should give me that 0.1894. A little bit off, but right, it's because we're in Excel, we can be more precise. We don't have to round to 2 decimals when we're looking up that z-value. And then I could do the rejection decision the same way I did with the other two, using that if statement. Any questions on this before we keep moving here? I'll show you something else one more time. I'm really going to try to kind of hammer in this. But let's say I go back to actually using the sample size of 20,000. So if I use this sample size of 20,000, much higher sample size, that's going to do what to this standard deviation? Divided by a larger number should decrease it. Now this denominator, right, is lower. So if I'm dividing by a lower number, what happens to my z-value? Divide by a smaller number, it should be getting larger. Seeing something the same distance away from my assumed true value is now going to be, if the standard deviation is smaller, a higher number of standard deviations away. So it's going to push this 0.88 out to whatever it was, 12.51, making that area in the tail much, much smaller, making my p-value really, really small. If my p-value gets smaller, what's it more likely that I'm able to do? It's more likely I can reject, right? It's going to be more likely it's less than these benchmark alphas. So I'll hit enter here. Sure enough, you know, my test statistic got larger. My p-value is basically 0. I can reject at every level now, right? But once again, I'm hammering this that like having these high sample sizes really gives us a lot of power to be able to reject certain values. So I think that should cover for today. I'll post this up on Canvas. You won't have any Excel stuff before this exam that's related to this. I was just kind of using it as a way to kind of show you how we do it in Excel and also kind of joining that with how we do it by hand. Okay. All right. So bring your questions on Wednesday. We'll do a lot more review. Like I said, probably go back to old stuff, but also still hammer some hypothesis testing. I won't be having office hours today. I'll get an announcement up on Canvas. I'll add more office hours later in the week if you're trying to finish up that Excel assignment. Okay. I'll see you guys on Wednesday.